This is APAB Calc. We're doing 2.2, which is basic differentiation rules, and example 6 and P6 are going to talk about trig. So, in the note cards that you made, hopefully you made note cards, and hopefully you're going to study your note cards, right? You made a bunch of note cards for different trig functions, right? And the differentiation rules for those trig functions. So, we're going to go ahead and start doing a few problems that involve trig, but fundamentally, you memorize the rule, and then it functions the same way as all of the other differentiation stuff that we've been doing. So let's look at example 6. So in example 6, we have a differentiation rule for cosine. Okay, so you have a note card for cosine, right? The only difference here is that there's a coefficient of 3 in front of the cosine, right? So if you have a 3 in front of the cosine, you just differentiate the cosine the same way you normally would, which would be a negative sign, but with that coefficient sitting in front. So my f prime of x is going to be 3 times negative sine of x. Now that's a little bit weird. You're probably not going to leave it that way. You'll probably write it as a negative 3 sine of x, okay? Don't write it as 3 minus sine of x. Like if you write this without the parentheses, then that minus symbol means subtraction, and that's not what you mean. You mean multiplication. So you could leave it this way. It would be a little odd, but you could. All right. For b, we're going to want to rewrite this first, recognizing that in reality, the sign has a coefficient of 1/5, right? This is a 1/5 in front of the sine of x. And so then it's the same basic problem as part A, where we're going to use a different differentiation rule that we have. Derivative of sine of x is cosine of x, right? But with a 1/5 in front. So my f prime of x is going to be 1/5 cosine of x. And that's great. And if you want to rewrite it as a cosine over 5, you could, but that'd be a little weird. And then finally for c, we're just using the fact that sums and products can be, sums and differences can be differentiated piece by piece, right? So my f prime of x is going to be the derivative of the x squared, which is a 2x, right? Plus a 4 times whatever the derivative of tangent is. Well, the derivative of tangent is secant squared. So 4 secant squared of x. And there we go. All right, so if you want to pause me, you can. I'm going to go ahead and walk through P6. If you want to do it ahead of me, you should probably stop me now. Cool. So, walking through P6. So, the derivative of secant, right? Derivative of secant is secant tangent, which hopefully you've memorized because you should be quizzing yourself. So, my f prime of x is just going to be a 10 in front of that secant tangent. And we usually say secant tangent even though technically it's secant of x tangent of x. You have to write the x's in it. We just usually say secant tangent. For b, I want to rewrite this as a 1/8 in front of the cosine of x. So my f prime of x is just going to be a 1/8 times the derivative of cosine. Well, the derivative of cosine is a negative sign, right? So derivative of cosine is a negative sign. So I know that when I derive this, I'm going to get a negative 1/8 sine of x. And again, if you want to do this thing here where you write the negative first and then clean it up, that's fine. But it's not awful to be able to just jump ahead and realize there's a negative in front of that. And then for this last one, right, same thing, I'm going to differentiate piece by piece, right? So my f prime of x is going to be an 18x squared, right? That's the derivative of this part, minus a 6 cosine of x, because that's the derivative of sine. And that's it, okay? Cool. All right, so let's talk about the last thing that we're going to talk about in 2.2, and then that'll be it for this section. And you'll notice that I did not throw in some of the differentiation rules that I gave you, like e to the x, a to the x, natural log yet, just because you don't necessarily need them for this particular section, but you should start studying them so that they're also in that sort of toolbox of things that you know how to do. All right, so the last thing we want to talk about is a derivative as a rate of change. So the last thing we're going to talk about is the derivative as a rate of change. Okay, so it shouldn't be a huge shock to you that the derivative, which is fundamentally a type of slope, right? Remember that derivative is like the tangent slope, right? So when you read derivative in your brain, you're going to be like, oh, hey, that's a slope, right? Because that's really what a derivative is. Fundamentally, it's a slope of a function. So it's not a shock that a slope, which is usually change in y over change in x, represents a rate of change, right? So, so we know way back when in algebra that slope was change in y over change in x, or y2 minus y1 over x2 minus x1, right? So it's not a shock to us that we frequently see in problems that slopes are, so in algebra word problems, right, you could spot the slope, by the word per, right? For instance, as an example, if I said a gym membership has a one-time fee of $50 and charges, let's say $18 per month, you can spot the slope by the word per, right? In this example here, our gym membership, right? So this would be my cost, would cost 18x, where x is a month, plus 50, because that's my y-intercept or my one-time fee, right? So it's not a shock that we're used to seeing slope as some unit per unit, right? So unit per unit, right? Meters per second, etc., etc. Okay, so the reason I mention that is that if we call, so if, for example, we use, let's use y of t equals, actually, we could even use h technically if you wanted, but, so let's use y of t equals the vertical position of, we'll say a ball, right? Like a ball that you've dropped, right? Or something that's dropping. So if I give you that y of t is vertical position, and let's just say that it's in, I don't know, we'll say feet. Sure. So we'll say it's in feet, right? So if I tell you that, and we'll say that t equals time in seconds, right? If I tell you that y of t is negative 16t squared plus 100, right? Then essentially what this is telling me is that for instance, y of 0 would be 0 plus 100, so 100 feet. What that means is the ball is being dropped at the start from 100 feet, which is pretty high up, right? Like 10 stories. This is some crazy egg drop in your physics class or something, right? But what's interesting about this, right, is if y is measured in feet and t is measured in time, then y prime of t is going to have units of, so y prime of t, right, is essentially going to be the change in y, which would be meters, or sorry, it wasn't meters, it was feet, would be feet per second, because it would be the change in the position, which is y, over the change in the time, which is t, right? So essentially, the derivative of this function, y prime, would be in meters per, feet per second, right? That's what I get for using the book, because I'm always a meters person. If you were to differentiate this, right, instead of x's, it has t's, but it's the same idea, you'd get negative 32t, right, plus 0, because the 100. So essentially, this derivative, right, if this thing was your position, then this thing is actually your velocity, right? And because it's the change in feet over, or change in distance over change in time, okay? So essentially, not only is this your velocity, but it's your instant velocity. Now, we're going to spend a lot of time talking about, or instantaneous if we want to be fancy. We're going to spend a lot of time talking about particle motion, which is essentially what this is. But the short answer is that if you want your instantaneous velocity, you'd need to use calculus and you want the derivative. So for instance, y prime of, I don't know, let's say, that's not a great number, let's say y prime of 1, right, would be a negative 32 times 1 in feet per second. What that means is that at t equals 1 second, the ball is moving negative 32 feet per second. And you might say, why is it negative? Well, that's because the negative is telling you it's moving down, right? The ball is dropping. So essentially this gives you your instantaneous velocity. Now, when I mentioned in 1.1 that calculus was the math of change and that calculus was what you needed to do higher level physics, until you learn calculus, you actually can't find the instantaneous velocity at which something is moving, which is a problem, because if all you can find is the average velocity between two times, like between a certain time where you stopped and another time where you stopped, or a certain time where someone measures a location and another measurement of location, you don't actually know details about the motion of something. So if you're trying to figure out the way that something's going to behave in space, or the way an airplane's going to work, or the way that some robot is going to behave, if you can't find exact values, if you can only find average values, then your answers are going to be inaccurate and kind of ruinous. It's not going to go well. So again, just to show you the difference, right? So if we wanted the average velocity from, let's do 2 times from t equals a to t equals b. Well, if you wanted that, you would just do old school slope. Okay, so you would do, in this case, my position was it would be y of b minus y of a, right? Because that's my change in position over my change in time, right? Because this would be in feet and this would be in seconds, and that would be my feet per second, right? But if I want the instant velocity, so instantaneous, if we want to be all fancy, instantaneous velocity, right? So this average velocity is something you can actually even do before algebra. Like you can do that in 3rd grade. You were probably at some point in your childhood required to measure 2 different positions at different times and then calculate velocity from that, and you could do it at a pretty young age. But your instantaneous velocity, well, that is the derivative. So if you want your instantaneous velocity at, let's say, t equals a, that's going to be y prime of a. And it's going to be feet per second still, but this is going to be the exact instant a is happening.